So coming back to that idea that for our ideal RF mixer, the intermediate frequency is proportional to the product of the RF and local oscillator inputs, let's take a closer look by assuming we have the following sinusoidal signals. Let's say we have some radio frequency signal, VRF, which is a function of t, is equal to, so we have some magnitude VRF times sine of omega, and then our omega is going to be at some radio frequency times t. We also have our local oscillator voltage, so VLO as a function of t, which also has some magnitude VLO sine omega t, where our omega is now going to have the frequency for our local oscillator. So what we're saying is that our VIF, our intermediate frequency voltage, should be proportional to the product of these two. So VRF of t times VLO of t. And so if we just take these two definitions we have written above, we can see that this is going to be equal to the product of the two magnitudes, VRF times VLO, and then the product of the two sine terms. So sine omega RF times t times sine of omega LO times t. And so looking at this, we can recall that we actually have a trig identity to help us deal with when we have two sinusoids being multiplied together by one another. So if we have sine of A times sine of B, that's actually equal to 1/2 times the cosine of quantity A minus B minus the cosine of the quantity A plus B. So using this trig identity, we can rewrite our VIF. We can say that VIF is function of t is equal to, now our magnitude is just going to be divided by 2, so we're going to have magnitudes VRF, VLO divided by 2, and now instead of having the two sine terms, we're going to have cosine of, and then our frequency is going to be the difference of the two, so omega RF minus omega LO, so the difference times t, and then we're subtracting cosine of, and then we have the product, or sorry, the sum of the two frequencies, omega RF plus omega LO times t, so we get something that looks like this. And of course, right here, we see this is our component of interest. So this is what we were looking at when we were talking about RF mixers in our previous video. We were talking about the difference between our radio frequency value and some local oscillator frequency. But what we notice is we actually have two frequency components. So we have this component that corresponds to the difference of the two frequencies, and we also have the component that corresponds to the sum of the two frequencies. And so what that means is if we're actually using this type of system, we're going to have some type of filtering so that we can get rid of this higher frequency term and just be left with the highlighted term, which is the one that we want. Another thing to note too is recall that our cosine function is even. So cosine is even, and so that means that really our frequency of interest here is our omega IF, which is just the magnitude or absolute value of that difference of the radio frequency minus the local oscillator frequency.